1.3 is on matrices and matrix algebra. So first, let's define a matrix. So here's the definition. So a matrix is an ordered rectangular array of numbers. So a matrix is an ordered rectangular array of numbers. And that's probably what you would guess or think about. So for example, you have the matrix A. Usually we use like A, B, C capitals as matrices. 1, 2, 3, 4. This would be a 2 by 2 matrix. And then B, say you had 1, 0, negative 1, 7, 0, 5, 2, 1, 1, negative 1, 3, 3, 5. And so it's always rows by columns. So you say there's 3 rows and 1, 2, 3, 4 columns. So it'd be a 3 by 4 matrix. So it's always M by N. So we say row by column. And we always, so the letters we use are M and N. So it's M by N, like that. The rows represent row vectors and the column vectors. So the rows represent row vectors. So that's how we want to kind of picture, interpret them now. The rows are row vectors and the columns, column vectors. Okay, so you get the idea there. So we could think of A now as, if we write the matrix like this, we could think of V and W, where V would be a row vector, so like 1, 2, and W would be 3, 4. W would be 3, 4. That. The general way of writing it is like this: A M by N, and we use this notation A sub I J, like that. And then the notation represent the rows and columns. So the first entry would be A11. Second entry, A12, so first row, second column, etc. And then you go down to A1N. Next one down is A21, and then the diagonal is, of course, the same. And then we go all the way across to A2N. We go all the way down to AM1. The mth row, first column would be there, and then this one, AM2, and then of course the last one would be MN, so it'd be AMN would be the last entry, like that. So this is an M by N matrix and matrix form. Okay, more definitions and stuff to begin with before we get into problems and things. So next definition is transpose. So we would call it the transpose of a matrix. So basically it's pretty simple. put this in quotes, you switch the rows and columns. So switch the rows and columns. Oops. Gotta move this up a little bit. Okay. So for example, you have the matrix A. I changed the matrix this time, I think, a little bit. 1, 2, 3, 4, 5, 6. And so the transpose would actually make that a different size matrix. So A transpose is equal to, and so you're switching rows and columns. So this becomes the first row becomes the first column. This row becomes the second column, like that. So I like to just like picture the row and just put it down. So 1, 2, 3, 4, 5, 6 is what I like to do. Like that. Another example. So if you had just this was a 2 by 3. So if you do the transpose on a 2 by 3, you get a 3 by 2. Obviously, transpose on a square on an n by n it would be square matrix. And if I haven't defined that, I'll do it right now. So oh, whatever. So I'll just tell you. Let's go back up here. Let's see. So n by n, we call that square for obvious reasons. Yeah, just to have it down there. Okay. So so I was going to show you like a vector. So if you had like a vector in a row, then it's transposed. This comes up a lot. So you have a vector, say like this, and it's 1, 2, 3. Then if you did the vector and you said like a transpose a transpose like that, let's write it down. So you do 1, 2, 3, and then it's transpose. Then you make that a column vector now. So that becomes, I put a 2 there. Why did I put a 2 there? So that transpose will just go across equals 1, 2, 3 as a column. So once you do the operation, then you go to the next spot there. So we represent a matrix often and not write the whole thing out. We often represent a general matrix, a general form like this. So we often do. So two matrices A equal to Aij and B equal to Bij are equal if they have the same size and each entry is the same. So are equal if they are, if they are the same size. So it would be m by n, or whatever that is, and each entry is equal. So the way you say that now is you just say A sub ij is equal to B sub ij. Now look how this is done. You can say for I 1 less than or equal to I less than or equal to m, because that's your first entry that corresponds to m. And then your second entry corresponds to j. So you'd say 1 less than or equal to j, less than or equal to n. M by n. Don't make those hats, by the way. Those are just i's and j's, so don't put a hat on there like a vector. Okay, moving on. Let's see. Definition of addition. I could probably fit it there. We'll just go to the next page. So addition of matrices. So definition, matrix addition. So we let A m by n equal A sub ij, and B, which notice that I have to say it's m by n, has to be the same size. Otherwise, it won't make any sense. You don't add different size matrices. Then if you say A plus B, this is pretty straightforward stuff here. You just add the entries. So A plus B of the matrix is each entry, you just add it up. A sub ij plus B sub ij, like that. So let's look at just a couple examples. So let's let A equal 0, y, t, and 4, and B equal 3, b, 4, and 1. Then if you add those up, and you were assuming that t and y and b are all represent numbers. So you have A plus B is equal to 3, y plus b, t plus 4, and 5. Scalar multiple. Next, just like vectors. So let's let C be a scalar. So let C be in the reals, like that. Then C times a matrix is you just multiply the components. Okay, so that represents the matrix, right? So you just bring it in just like you'd expect. Like that. Excuse me. Okay, so let's look at an example of that. So if we let A equal 1, 2, 3, 4, and let's say we multiply by, 3. So 3 times A is equal to 3 times that whole matrix, 1, 2, 3, 4. I'm going to just show this once. Then we'll just multiply next. It's 3 times 1, 3 times 2, 3 times 3, and 3 times 4. And that equals 3, 6, 9, and 12, of course. Okay, so far so good. So addition and scalar multiple, that's easy stuff. The next is multiplying matrices, not as necessarily simple. I'm going to move this over here. Not as simple, but hopefully you've seen it before. And I don't know, I don't know if I had when I took this class or equivalent type of class. I think it might have been the first time I multiplied matrices. So I will make that assumption too, that you've never seen matrix multiplication. If you have done algebra, college algebra, you probably should have at least. But it depends on kind of how you got to here. So this is on matrix multiplication. This one's not as obvious. So let's let A be our same stuff. So you say, so let's let A be m by n. So that's A sub ij. We will talk about that. And B be in by P. So the these have to match. So your columns of the first one has to match the rows of the second one. And so this one, oops, I forgot to write this out. This one we'll write as B sub ij. Then A times B will be M by P. And I didn't really need to write it like, no, that's fine. We'll leave it like that. Because it's a matrix, but that product gives us C sub ij. Then we define that, which is not obvious in this definition, but then we'll show you how to do it. Where C sub ij is equal to the sum as k goes from 1 to n of A sub I k B sub k j. So what that looks like as a sum, each entry is AI1 B1j plus AI2 B2j, etc. Till you get to the end, which is AIN and then BNJ. So each entry has that form. So let's look at an example. Let's let A equal 1, 0, 3, 2, 1, 4, 0, 5, 2, and B equal 1, 2, 3, 4, 5, 6. Not very interesting, huh? Okay. So this is a 3 by 3 matrix, and this is a 3 by 2 matrix. So the resulting matrix ends up being the outsides, ends up being, this is the resulting matrix. So these have to match. So let's see, this is the resulting matrix, is 3 by 2. And then these have to be equal or match. So those are equal, and this outside is the result. It's like what you get. Okay, so let's look at that product down here. So A times B. So you write down all of A. So 1, 0, 3, 2, 1, 4, 0, 5, 2, and then times 1, 2, 3, 4, 5, 6. Just think of what I had. Okay, so then when you do this product, you go, I'll try to do this as highlights here. So you go, we'll use those colors in that order. So you go across and down is your first entry. So it's 1 times 1. I'll do the product in my head, or we'll do the product, but then let's not add it. So you do 1 times 1 plus 0 times 3 plus 3 times 5. So you get 1 plus 0, go ahead and put that in, plus 15. So that's this entry. Then you go across and down here. So you stay on the first row and then stay on the first row and then down. So you go, so let's try it again. So you go here and here, it's your first entry. Your second, you're going across to here is your second entry. So you go across and down is over here. So that becomes 2 plus 0 plus 18. And we know our resulting matrix will be a 3 by 2, so I always put that down to remind myself. Okay, then that was this one. Okay, so then you go to the next one down, and you go across and down. So that's 2 times 3 times 20. Or I'm sorry, 2 plus 3 times 20. 2 plus 3 plus 20. Okay, so that's this one. And then you go across and down to the next one. Excuse me. So that's 4 times 4 plus 24. Okay? And then that was this one. And then next, you go you're down to the next one. You go across and down. And that'll go here. And then you do it again. Let's try to do what? Purple? Are we on purple? Let's do blue. Then you go across and down, which goes here. So you get 15 plus 10, 0 plus 15 plus 10. And then you get 0, I'll put in 0, 0 plus 20 plus 12. Zero plus it's messing up because of my hand. It's 0 plus 20 plus 12. It's sometimes more difficult to explain this stuff than to just do it, obviously. Okay, so that's your matrix multiplication. And then you, of course, multiply it all out, and you get whatever result that is. So it's, I'll just write out what I got. I got 16, 20, 25, 32, 25, and 32. Okay, which is a 3 by 2 matrix. All right. Now, you need to be able to do this by hand a couple times, show all your work, but you can use a calculator or anything, any sort of program that'll do matrix multiplication. Later on, we'll do row reduction, and so you can use that. But for this, you need to know how to do it, because we'll do it in general for stuff and see how things multiply, and you need to know the basic concept. So practice it a number of times by hand, but your backup will be to test and verify with a calculator or a computer program. All right, let's see. Okay, next is a couple examples, some simple cases to show you some ideas here. Next example, let's let A equal 1, 2, negative 1, 3. And B equal 0, negative 1, 2, 4. Then what I want us to do, this is something I'd always have you do in class, I want you to do the product A times B and B times A, and then draw a conclusion. So 1, 2, negative 1, 3. And then 0, negative 1, 2, 4. Okay, do that product and then do B times A. So you can pause this whole thing and go for it right now and work it out. Like that. So do the product, see what you get. I'll write down what I have without like showing you the details. So I get 4, 7, 6, 13, 1, negative 3, negative 2, 16. So these are square matrices, so rows and columns aren't really a big deal. What type of conclusion can you draw because of this? You get A times B versus B times A. What are you getting? They are not equal. Exactly. Yes. So this is, you may conclude that therefore matrix multiplication, and technically it'd have to be square, otherwise it's kind of moot. Square matrix multiplication is not what? Is not commutative. All you need is one counterexample, right? So I showed you one counterexample. They have to be square matrix, otherwise the rows and columns won't match up. But it's very clear that matrix multiplication, you do not get the same thing. Therefore, we conclude is not commutative. Okay. Because of that, you don't get this situation. This is an idea called cancellation. So let's talk about that a little bit. Okay, so cancellation. What does that have to do with? So let's let A, B, and C be real. If A times C equals B times C, well, okay, these are just real numbers, right? So if we have this as a real number, right, this is then like, you have 2 times 4 equals 2 times 8 kind of thing. So if A times C is B times C, then what can you conclude? Then we have what's called cancellation. You divide both sides by C, and you get A must equal B. If it's 0, then you get 0 equals 0 and you're done. So you get A equals B. That's what we mean by cancellation. Okay, so these basically cancel. Now, not a good terminology. I don't like that at all, but that's what we kind of call it. So the question is this: if matrix, okay, so actually be a little more careful. We're not just in college algebra anymore, or Cap 1. So now let capital A, B, and C be matrices. So the question is, if A times C equals B times C, then does this imply that A equals B? Okay, so that's the question. That's the idea. Well, we can use I did another example. So let's use this example to show that. You might already have an intuition about that. So A times C. So let's do an example here. So to prove something is true for everything, that takes that you need to do some techniques in general. But to show something's not true, all you need is a counterexample. So let's see. Where am I at? Okay, so let's look at this example. Let's let A equal 1301 and B equal 2423. And C equal 1, -2, -1, 2. Then let's calculate the first part. Let's calculate A times C. And let's calculate B times C. Okay, so do that either in a calculator. Now's maybe a good time to figure that out. Or a computer package on your phone or something. Doesn't really matter. And do that product. I mean, you're just doing A times C, so it's 1 plus -3, and then -2 plus 6, etc. So you get -2, 4, -1, 2, -2, 4, -1, 2. Now, what is that? So those are equal, right? So here's the question, right? A times C equals B times C. Yes, right? So those are the same product, yet what do you know about A and B? If you had cancellation, you would be able to conclude A and B are the same, and they're not, right? Those are not the same. So we have A times C equal to B times C, yet A does not equal B. So that it means, or therefore, there's no cancellation property. For matrices. Not all the time. Now, there will be situations where we do get that kind of a property, but that will be a little later. That'll be, well, okay, I don't want to go too far ahead, but that's inverse matrices and stuff. So we'll talk about that later. Couple more definitions. We'll get to properties here of matrices in a little bit. Might be the next video. Yeah, I'll probably do one more after that. But let's go ahead and define identity matrix and zero matrix. Pretty easy stuff, and then we'll stop. So, identity. So what's the identity for real numbers? Right, it's the number 1, right? The identity for real numbers is 1. It's what you multiply and get the same thing back. So identity matrix is just basically a matrix, not with all ones. That's not it. We call identity matrix of order n. And you say I sub n. And it's basically 1 along the diagonal, and then zeros everywhere else. So it would look like that, and then a 0, like that, and then another 1, 0, and then it says 0, and all the way down, and then you get a 1 diagonal. So it's ones on the diagonal. When that happens, I have my hand in the wrong spot down there. Freaks out. Ones on the diagonal and zeros elsewhere. All right, so just a little example here, simple one. Okay, so we have, right, so we want to have a times 1 equal to 1 times a, which is equal to a, right? That we want that to be true for all real numbers, a, and then 1 is the multiplicative identity for real numbers. So let's just use the matrix A, 1, negative 1, 3, 2. And let's do a product. So it'd be 1, 0, 0, 1. So just to do this on your own. And then 1, negative 1, 3, 2. What do you get? When you do that product, or do that, like literally do that product, see what you get. And you'll see you get the same thing back. I just don't want to go through all those little steps again, but you go 1 times 1 plus 0 times 3, so it's just 1. 1 times, okay, so 1 times negative 1, 0 times that, so it's just that puts it back. 0 times 1, 0. 1 times 1 is 3, puts it there. So you see how that works? And then if you did the other direction, it also works. So if you did 1, if you did 1, negative 1, 3, 2, if you commute that with the identity matrix, that has to work. And that, of course, will work as well. You get the same matrix back. So again, check that. You got to do these on your own, by hand a few times to see what's going on. Okay. Next, last thing before I go into the properties is the zero matrix, just like zero vector. Now the zero matrix is a matrix of all zeros, so don't have to worry about that one. Identity matrix. Zero matrix, we often just use like an O, and it's M by N, and that just has all the zeros in it, right? So and that's the zero matrix. Any size, M by N. The zeros in the reals. I'm not sure what else to say about that. So that's the identity for addition. So this is basically A plus 0 is 0. So 0 plus A plus 0 is 0. I mean, A, not 0, is A. And also, there's times when you can add matrices and you get the additive identity. So this is the we call it the zero matrix, but it's basically the additive identity for matrix. It's what you add when you add additive inverses, opposites. You get 0. Well, we'll get the zero matrix, and that'll be true in the properties because we have the zero matrix. All entries are real numbers. We'll have multiplicative identities. For the identity element, this is called the identity element of a set of matrices. But do we have always multiplicative identities? Is there always an inverse that you multiply and gives you 1? That's really one of the questions too. And I'll skip that for now. You could ignore that little piece because it's gets into the inverse matrices concept, which we'll get to later. Okay, we'll go on. We have properties to do, properties of transpose, a few proofs on transpose, and then that's it for 1.3. So a little shorter video next.